Section I. Introduction. We're going to discuss the potential misuse of large language models, LLMs, such as ChatGPT, Claude, or the open source Llama. As these models become more accessible and powerful, they could be used to create fake news, impersonate individuals, facilitate scams, or even disrupt student assessments. It's crucial that we find ways to regulate and monitor their use responsibly. However, this is challenging because it's hard to tell the difference between text generated by these models and text written by humans, whether we're using human judgment or algorithms. One potential solution is watermarking, a technique that's been explored for both image and text generation models. Watermarking subtly changes the process of generating samples or the probability distribution of the generated tokens, leaving a nearly invisible trace in the generated text. Then, a detection mechanism can analyze the generated tokens to see if their distribution matches the one created by the watermark. In this paper, we're going to make three main contributions to the existing research. Firstly, we're going to address the issue of false positives. These can have serious consequences, such as wrongly accusing someone of spreading fake news or cheating on an exam. Current research tends to focus on sensitivity, the true positive rate, or TPR, rather than specificity, which is related to the false positive rate, or FPR. However, the FPR hasn't been thoroughly tested on a large scale, with more than 1,000 negative examples. Our large-scale experiments show that the assumptions made in previous studies don't hold up, and that their detection thresholds underestimate the number of false positives at low FPR. We're going to provide statistical tests that can theoretically guarantee false positive rates and accurate p-values in real-world situations. We'll validate these tests empirically and show that they can almost perfectly control the FPR. Secondly, we're going to compare different watermarking methods and analyze how watermarks affect traditional natural language processing, NLP, benchmarks. Current evaluations of watermarks mainly consider how much they deviate from the original LLM distribution, often using a measure called perplexity. However, this contrasts with how LLMs are usually evaluated, which is based on their practical usefulness, such as their performance on free-form completion tasks like answering questions. We believe that this kind of evaluation provides more useful information about how the model performs on real-world tasks. Lastly, we're going to extend these algorithms to more advanced detection schemes. When we have access to the LLM at the time of detection, we can provide optimal statistical tests. We'll also look into multi-bit watermarking, which involves hiding binary messages as watermarks. This is a step up from current approaches, which only deal with 0-bit watermarking. This will allow us not only to determine whether a text was generated by a watermarked LLM, but also to identify which version of the model generated it. Section Summary. The misuse of large language models, LLMs, like ChatGPT or Llama can pose threats such as generating fake news, facilitating scams, or impersonating people. Enforcing fair usage through regulations and technical means is important, but monitoring LLM usage is challenging due to the difficulty in distinguishing generated texts from real ones. This paper introduces statistical tests to control false positive rates, compares watermarking methods on NLP benchmarks, and expands detection schemes to identify the version of the model that generated the text. Section 2. Technical background. Let's delve into the technical background of this paper. Firstly, we'll discuss large language models, or LLMs for short. These are a type of neural network that generate text by calculating the likelihood of producing a sequence of words or characters, given a certain context. This paper specifically looks at decoder-only models, also known as autoregressive LLMs. In these models, the words or characters are represented as tokens, which are elements of a vocabulary set. Given a context, the model estimates the probability of each token being the next in the sequence. It does this by computing a vector of logits, which are then transformed into probabilities using a function called softmax. The softmax function is controlled by a parameter called temperature. To generate a sequence from a given context, the model samples a token from this probability distribution, adds it to the context, and repeats the process. There are various methods for sampling tokens, including greedy search, beam search, top K sampling, and nucleus sampling, also known as top P sampling. Next, we'll discuss the concept of watermarking in text generation. We'll consider two types of watermarks, those that modify the distribution of tokens, and those that modify the sampling process. When modifying the distribution, the original distribution, which we'll call P, is replaced by a similar distribution, Q. This new distribution, Q, is a function of P, and a secret key, K. In this case, the secret key is used to partition the vocabulary into two sets. One set, called the green list, contains a certain proportion of the tokens. The likelihood of each token in the green list is increased by a certain amount, and the softmax function then outputs the new distribution, Q. This encourages the model to generate tokens from the green list more frequently. However, on average, across all possible keys, the watermarking process doesn't bias the distribution. To detect the watermark, the text is tokenized and the number of tokens in the green list is counted. More formally, for a text of T tokens, the score is the number of green list tokens. Section summary. Large language models, LLMs, are neural networks that generate text by estimating the probability of generating the next token given a context. This paper focuses on decoder-only models and discusses two types of watermarks: modifying the distribution or the sampling. Watermarking modifies the original distribution by replacing it with a similar distribution, encouraging the generation of specific tokens without biasing the overall distribution. Detection involves counting the number of green list tokens in the generated text. Section 2b2 Modification of the sampling, 1.7. We're going to discuss a modification to the traditional sampling methods used in watermark embedding. Instead of using the usual sampling schemes, we use a more predictable process. For example, we select the next token by calculating a value, which we'll call x(0). This value is determined by finding the maximum value of a certain function that depends on a distribution, represented by p, and a secret vector, represented by r. This secret vector is generated from a secret key, k. This method encourages the generation of tokens that have high values for both r and p. An interesting feature of this method is that it doesn't bias the distribution on expectation over the secret vector. This means that the probability of a certain event, represented by x(0) equals v, is equal to the value of p for all values in the set v when the secret vector is distributed uniformly. To detect the watermark, we calculate a score for t tokens. This score, s_t, is calculated by summing up the natural logarithm of 1 minus the value of r for each token. We can adjust the balance between the quality of the generation and its robustness by changing the strength of the watermark. In one method, increasing a parameter we'll call delta leads to the generation of more green tokens, but it also increases the risk of including unlikely tokens. In another method, increasing a parameter we'll call theta has the same effect because it reduces the relative importance of p over r by flattening the probability vector. The secret key, k, which generates the green list or the sampling of r, needs to be diverse. Using a fixed key can lead to security issues and biases in the text generation. One solution is to make the key dependent on time, t. This means that the secret key changes from one token to another. However, this can cause synchronization issues during the detection stage, for example, when a sentence is deleted. A common practice to ensure self-synchronization is to make the key dependent on the window of h previous tokens. This secret key is then used to initialize a random number generator, rung, at time t. The RNG is then used to generate the green list or to sample r. The width of this window defines a balance between the diversity of the key and the robustness of the watermark. In a specific case where h equals 0, the key is the same for all tokens, which makes the watermark particularly robust to text editing. Section summary. The watermark embedding in the sampling process replaces traditional schemes with a deterministic process, encouraging the generation of tokens with high values for both the secret vector and the distribution. The detection stage computes a score based on the logarithm of the difference between 1 and the product of the secret vector and the token's value. The trade-off between generation quality and robustness can be adjusted by varying the watermarking strength, and the secret key used for watermarking should have wide diversity to avoid security issues and bias in text generation. Section 2EZ Test. We're going to discuss a method for detecting whether a piece of text has been artificially generated or watermarked. We'll be comparing two possibilities. The first, referred to as H0, is that the text is naturally written by a human or without any watermark. The second, H1, suggests that the text has been generated with a watermark. To make this distinction, we use a statistical method known as the z-test. This test helps us determine if the average score of a sample differs significantly from what we'd expect if the standard deviation is known. The z-test calculates a value known as the z-statistic, which is the difference between the average score per token and the expected average score under H0. Divided by the standard deviation per token under H0, all divided by the square root of the number of tokens. The z-test is typically used when we have a large number of samples and we assume that these samples follow a normal distribution under H0, thanks to a principle known as the central limit theorem. This assumption is crucial for calculating the p-value, which is the probability of observing a z-value as extreme as the one we've observed, assuming h0 is true. If the p-value is less than a predetermined false positive rate, FPR, we flag the text as watermarked. We've tested this method on a small scale, with around 500 samples. Now, we're going to conduct a larger study to validate our approach. We'll use 100,000 texts from multilingual Wikipedia to represent a wide range of natural text. We'll cut 256 tokens from each text and run the detection tests with varying lengths for the context window used when seeding the random number generator. We'll repeat this experiment with 10 different master keys, resulting in 1 million detection results under H0 for each method and context window length. For detecting the watermark, we'll use a value of 0.25 for gamma. Our initial observations show that the theoretical false positive rates don't match the empirical ones. The actual false positive rates are much higher than the theoretical ones. We've also noticed that the distributions of p-values aren't uniform, which they should be under H0. Furthermore, the larger the context window for watermarking, the closer we get to the theoretical guarantees. However, in practice, we would need a significantly large context window to get reliable p-values, but this makes the watermarking method less robust to attacks because it affects synchronization. Section summary. The z-test is a statistical hypothesis test used to determine if a sample mean significantly differs from its expectation. It computes the z-statistics based on the expectation and standard deviation under the null hypothesis. However, empirical studies have shown that the theoretical guarantees of the test do not hold in practice, as the empirical false positive rates are higher than the theoretical ones. Additionally, larger watermarking context windows are needed to obtain reliable p-values, but this compromises the method's robustness to attacks on generated text. Section 3b. New non-asymptotical statistical tests. We're introducing new statistical tests that don't rely on the Gaussian assumption, which often fails for short texts. These tests help to narrow the difference between the observed and theoretical false positive rates, FPR, particularly for low FPR values, as illustrated in the figure. Firstly, we'll discuss the approach by Kirschenbauer and colleagues. Under the null hypothesis, we assume that a certain event, represented by x(t), being part of g_k(t), happens with a probability denoted by gamma. We also assume that these events are independent and identically distributed. Therefore, the score s_t follows a binomial distribution with parameters t and gamma. Let's consider a text under examination with a score of s. The p-value, which is the probability of getting a score greater than s under the null hypothesis, is calculated using a formula that involves the regularized incomplete beta function. This function is used to express the cumulative distribution function of the binomial distribution. Next, we'll look at the method proposed by Aronson and colleagues. Under the null hypothesis, we assume that the text under examination and the secret vector are independent. This leads to the score s_t following a gamma distribution with parameters t and 1. The p-value associated with the score s is calculated using the upper incomplete gamma function. Under the alternative hypothesis, the score is expected to be higher, which means the p-value is likely to be small. However, even with these new statistical tests, the observed FPRs are still higher than the theoretical ones, which raises concerns about the reliability of the detection. Kirschenbauer and colleagues point out that random variables are only pseudo-random because repeated windows generate the same secret. This can occur even in short texts, especially in formatted data. For example, in a bullet list, the sequence of tokens, n repeats frequently. This repetition undermines the assumption of independence necessary for calculating the p-values. To address this issue, we experimented with two simple strategies at the detection stage. The first strategy only considers a token if the watermark context window hasn't been seen before during the detection. The second strategy scores the tokens for which the combination of the watermark context and the current token hasn't been seen before. The second strategy is more effective as it counts more n-grams, leading to a better true positive rate, TPR. It can also handle the specific case of h=0. When we chose not to score previously seen combinations of watermark context and current token, the observed and theoretical FPRs matched perfectly, except for the case where h=0, where the FPR was slightly underestimated. In conclusion, we can ensure a reliable FPR by using new statistical tests and by only scoring tokens for which the combination of the watermark context and current token hasn't been seen before. Section summary. The section discusses new non-asymptotical statistical tests for short texts, which reduce the gap between empirical and theoretical false positive rates, FPR. Two methods are presented. one based on a binomial distribution and the other on a gamma distribution. However, even with these tests, the empirical FPRs are still higher than the theoretical ones due to the repetition of certain sequences in the text. To address this, two heuristics are proposed: considering a token only if the watermark context window has not been seen before, and scoring tokens for which the watermark context plus the current token has not been seen before. These heuristics improve the true positive rate, TPR, and ensure FPR by avoiding the scoring of already seen sequences. Section IV: A robustness analysis. In this section, we'll be comparing different watermarking methods by looking at their true positive rate, TPR, when identifying watermark texts. To do this, we use statistical tests and a scoring strategy we've previously discussed. We consider a text as watermarked if its p-value is less than 1 in 100,000, which ensures a false positive rate, FPR, of the same value. For our experiments, we're simulating a chatbot scenario. We use Guanaco 7B, a version of Llama that's been fine-tuned for instruction, and prompt it with the first 1,000 prompts from the alpaca dataset. We generate responses using top P sampling with a probability of 0.95, and in cases where the temperature is 0.8 and gamma is a quarter. We also simulate attacks by randomly replacing words with a 30% chance. Our results show different behaviors for different watermark strengths. For example, one method provides a finer control over the balance between watermark strength and quality, with TPR values ranging from 0 to 0.9. Another method is more consistent but can't achieve a TPR higher than 0.8, even when the quality is significantly reduced. The width of the watermark context also has a significant impact. When it's low, we see more repetitions because the generation is easily biased towards repeating certain words. This leads to lower quality scores and unusable responses. However, a low width also makes the watermark more robust. It's also worth noting that the width influences the number of analyzed words, as we only score words that haven't been seen before. If the width is high, almost all these words are new, while if it's low, the chance of repeated words increases. Next, we look at the impact of watermarks on free-form generation tasks. Previous studies have measured the impact on quality using metrics like perplexity or similarity score. However, these metrics don't tell us much about how useful the model is for real-world tasks, which is where the true value of language learning models, LLMs, lies. Watermarking LLMs could be harmful for tasks that require very precise answers. So, we're going to quantify the impact on typical natural language processing, NLP, benchmarks to assess the practicality of watermarking. LLMs are usually evaluated by comparing samples of plain generation to a set of target references or by comparing the likelihood of a predefined set of options in a multiple-choice question format. The latter doesn't make much sense in the case of watermarking because it only affects sampling. So, we're limiting our evaluations to free-form generation tasks. We use the same evaluation setup as Llama, which includes closed-book question answering, mathematical reasoning, and code generation. For one method, we apply the distribution shift before greedy decoding, with a delta of 1.0. For another method, we apply top P at 0.95 to the probability vector, then apply the sampling given by the algorithm. Our results show that the performance of the LLM is not significantly affected by watermarking. The distribution shift approach is slightly more harmful than the sampling-based one, but the difference compared to the original model is small. Interestingly, this difference decreases as the size of the model increases. Models with higher generation capabilities are less affected by watermarking. This could be because the larger models have a better global distribution and are thus more robust to small perturbations. Overall, evaluating on downstream tasks shows that watermarking may introduce factual errors that are not well captured by perplexity or similarity scores. Section summary. In this section, the authors compare different watermarking methods by analyzing the true positive rate, TPR, when detecting watermark texts. They use statistical tests and scoring strategies to flag a text as watermarked. They also evaluate the impact of watermarks on free-form generation tasks, such as question answering and code generation, and find that the performance of the language models is not significantly affected by watermarking, especially for larger models. However, watermarking may introduce factual errors that are not well captured by traditional evaluation metrics like perplexity or similarity scores. Section V. Advanced Detection Schemes. We're now going to delve into some advanced detection schemes. These are enhancements to the detection methods we discussed earlier. Firstly, let's talk about the Neyman-Pearson and simplified score function, which is specific to the scheme developed by Aronson and his team. Under one hypothesis, denoted as H0, we have a random variable RV that follows a uniform distribution between 0 and 1. However, under a different hypothesis, H1, this random variable follows a beta distribution with parameters 1 over PV and 1. The optimal Neyman-Pearson score function can be calculated as the sum of the natural logarithm of the ratio of the probability density function under H1 to the probability density function under H0, for each observation from 1 to t. This can be simplified to the sum of the quantity 1 over px, t, minus 1 times the natural logarithm of rx, t, plus a constant a, for each observation from 1 to t. Here, a is a constant that doesn't depend on r, so we can ignore it. However, there are two issues with this approach. Firstly, to detect, we need to compute px, t, using the LLM. Secondly, there's no simple formula to calculate the p-value. We can address the second issue by using a Chernoff bound, but this doesn't guarantee accuracy. Our experiments show that this detection method gives very low p-values for watermark text. However, these p-values are fragile and any attack can increase them to the level of the original detection scheme, or even higher. An alternative approach is to remove the weighting. In this case, the score function is the sum of the natural logarithm of rx, t, for each observation from 1 to t. The p-value can then be calculated as the ratio of the incomplete gamma function of t and s to the gamma function of t. However, in our experiments, this score function doesn't perform as well as the original detection method. Now, let's move on to the theory. It's relatively straightforward to convert a 0-bit watermarking scheme into a multi-bit watermarking scheme. We can do this by associating a secret key with each message. The decoding process involves running detection with each key, and the decoded message is the one associated with the key that gives the lowest p-value. The overall p-value then becomes 1 minus the quantity 1 minus p raised to the power of m, where m is the number of possible messages. However, running detection for m keys is expensive, as it requires generating m secret vectors. We can overcome this by ensuring that the secret vector associated with each message is created as a circular shift of m indices. By generating the initial secret vector as a d-dimensional vector, where d is greater than or equal to the size of the token vocabulary, we can embed up to d different messages. We do this by only keeping the first dimensions of each circularly shifted vector. This means that the number of messages can be greater than the size of the token vocabulary. Furthermore, the scoring functions can be rewritten as sums of dot products. This allows for parallel computation of all m scores, similar to the fast Fourier transform, FFT, method. However, since correlation with the one-hot vector is also equivalent to a circular shift, FFT is not needed and scores can be efficiently obtained via a cyclic shift operation. The first m components of the score are the scores for each message. Section summary. In this section, the authors propose improvements to the detection schemes presented earlier. They introduce the Neyman-Pearson score function and show that it can be optimized for detection. However, there are two drawbacks: the need for the LLM to compute certain values and the lack of a closed-form formula for the p-value. The authors suggest an alternative score function that removes weighting, but it does not match the original detection. Additionally, the authors discuss the extension of 0-bit watermarking to multi-bit watermarking by associating a secret key per message, and they propose a method to efficiently compute scores for multiple keys. Section VB2 Experiments. We conducted experiments in a tracing scenario where the message is either a user's identifier or a model version. The aim is to determine whether a particular user or model produced a specific text detection, and if so, identify which one, identification. There are three types of errors we could encounter: false positives, where a regular text is incorrectly flagged; false negatives, where a watermark text is overlooked; and false accusations, where a watermark text is flagged but the wrong identifier is selected. In our simulation, we had 1,000 users, each generating 100 watermark texts using the Guanaco 7B model. We can extend the accuracy beyond these 1,000 identifiers by adding more identifiers that don't have any associated text, resulting in a total of more than 1,000 users. We used nucleus sampling with a top p-value of 0.95 for text generation. For some parameters, we used a delta value of 3.0, a gamma value of 1/4, and a temperature theta of 0.8. For others, we used a theta value of 1.0. In both cases, the context width was 4. A text is considered watermarked if its score exceeds a certain threshold set for a specific global false positive rate. The source is then identified as the user with the smallest p-value. Our results show that watermarking allows for identification because it performs well enough to deter misuse. For instance, among 100,000 users, we were able to correctly identify the source of a watermarked text half of the time while keeping the false positive rate at 1 in a million, provided the text wasn't tampered with. At this scale, the false accusation rate was 0 because we set the threshold high to avoid false positives, making false accusations unlikely. However, as the number of users increases, the identification accuracy decreases because the threshold needed to prevent false positives also increases. In essence, by allowing multiple messages to be encoded, we sacrifice some detection accuracy in exchange for the ability to identify users. Section summary. In the VB2 experiments, the goal is to determine if a given text was generated by a specific user or model. 3 types of errors can occur: false positives, flagging a normal text; false negatives, missing a watermark text; and false accusations, flagging a watermark text but selecting the wrong identifier. By simulating multiple users and using watermarking techniques, the source of a watermarked text can be successfully identified with a low false positive rate, although the identification accuracy decreases as the number of users increases.